Hello and good day. My name is Amar bin Muhammad Sulfanis from Group 21, and we will present our findings from our analysis of the hood and duct exhaust system typically found in commercial kitchens using ANSYS Workbench software. The flow of this presentation will be as such. The first is the introduction, including the problem statement, hypothesis, and objectives. Second will be showcasing the model and the methodology of our own project. Thirdly will be the results and discussions of the analysis with disclaimers and possible caveats as presented by other members. And finally, the conclusion.
This is our group member consists of four people. Amar bin Muhammad Zulfanis as a group leader, Muhammad Samir bin Tundreng, Muhammad Faris Akmal bin Fatun Nizam, and the last one is Muhammad Yunus Nabil bin Abdul Latif.
Now, without further ado, I will start first. Industrial exhaust systems are there to protect workers from harmful contaminants while keeping the equipment safe. But there's a problem. Many of these systems waste energy due to outdated designs. Industry studies shows that optimizing simple parameters like duct bands and flow rates can cut energy use by up to 40%. Today, we will use CFD to find the most optimized design for an efficient exhaust design. The purpose of this project is ultimately to optimize industrial exhaust systems by analyzing the degrees of duct bands and the flow rates determined in the software using CFD, which is ANSYS. Why? Because based on the US Department of Environment, energy waste in HVAC is around 20 to 30% of industrial use. So this is an important matter to discuss. Moving on to problem statement. Despite the importance of exhaust systems, there's two critical gaps that persists. First is the lack of data on how band angles directly impact pressure losses, especially for the 90 to 45 degree ducts, based on a study in 2013. Unoptimized duct geometries and excessive flow rates waste energy while compromising containment. Optimizing exhaust hood jet parameters and exhaust rates can enhance pollutant capture, while also reducing energy waste from excessive airflow, based on a study in 2024. And based on a guideline book in 2013, standard 90-degree duct bands have higher bend coefficient than gradual bands, which affects pressure drop. We hypothesize that smooth duct geometries reduces pressure drops compared to sharp configurations, whilst higher velocity decreases temperature within the duct. Therefore, our objectives in this project is to measure and compare pressure drop and airflow velocity between the different duct band angles, mainly 45 degrees, 90 degrees, and 180 degrees. And to a certain extent, if the software allows us, we will study the temperature distribution within the duct. That is all from me. Thank you.
Hello, I am Muhammad Yunus Nabil and I'll be presenting on the model, the mesh, and the conditions. Firstly, the models are done in Autodesk Inventor for ease of access on editing. The model consists of three different parts: the extractor funnel, ducting, and hood. There's three types of ducting in order to examine the three types of flow in types of bands of ducting. There's the 180 straight ducting, 45-degree band ducting, and 90-degree band ducting. Each ducting has an opening of 230 mm by 380 mm and a total length of 200 millimeters. Next, the ducting is then the models are then assembled into three different assemblies. There's the first assembly for the 180, second assembly for the 45 degree, and also the assembly for the 90-degree band. Now for the mesh and its conditions. After creating the mesh is then converted into three named bodies: the outlet exhaust, where the flow ends for the simulation, the inlet funnel, where the flow begins for the simulation, and the wall constraint, where most of the analysis is done. This wall constraint acts as the border and the direction for the flow. It is airtight to ensure that the flow simulation is within the duct, and this is where the stagnation of the flow is examined, the change in temperature, and also the change in flow. Now, the constraint and variables set on the simulation are that there are three separate simulations for each individual models set at the different velocities of 7.9 millimeter per second, 23.6 millimeter per second, and 39.9 millimeters per second. The temperatures for each simulations are set at 30 degrees Celsius with a pressure of 0 pascals to simulate atmospheric temperature. Now, the definition of the mesh is set at a moderate scale in order to run the simulation smoothly. The walls are set to be a non-slip surface so that the flow can be easily examined without friction, and the flow is also set to be adiabatic. The simulation graphics rendered are for the flow velocity, temperature gradient change, and also for the model overall. As you can see, these are the three meshes of the three models. They are set at moderate scale so that the simulation can run smoothly.
Okay, so Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faris Akmal. So today I would like to explain briefly about our CFD project result regarding the project about the exhaust fans or air duct in the kitchen. Okay, so for the result, the first one, I would like to show the pressure control for this project. So as you can see, we managed to do three different models for three different velocity. Okay, so the first one is at 90 degrees. The second one is slightly bent at 45 degrees, and the third one is straight one. Okay, or 180 degrees. And the velocity that we choose as the initial was the 7.9, 23.6, and 39.3. Okay, so as we can see in the table, uh, the pressure drop for 90 degrees quite significant compared to 45 degrees and 180 degrees. Okay, so the pressure drop is actually the pressure in the inlet minus to pressure in the outlet. All right. So the next one is velocity vectors. So again, the same model, the 90 degrees, 45 degrees, and 180 degrees with the same initial velocity. Okay, and we can see that the 90-degree model, 90-degree exhaust fan, again, reduce the maximum velocity vectors inside the exhaust, the air duct. Okay. Okay, so for discussion, we have chosen two different questions to be answered. The first one is the quantitative effect of duct bend angles on pressure drop and airflow velocity. Okay, so bend angles in duct systems affect pressure loss, especially at higher airflow speeds. Sharper bends like 180 cause more turbulence and resistance, while 45 degrees maintains smoother flow and better efficiency. Okay. Okay, the next one is temperature distribution under varying airflow velocities. Okay, so the airflow speed affects how heat is spread in the duct system. At low speed, heat will build up on the walls and causing uneven and higher temperatures. So as speed increases, the convection improve, spreading the heat more evenly and lowering the temperature. Okay, so, by improving the speeds, ducts cool more efficiently, reducing hot spot and thermal stress. Combined with smooth bend, like 45 degrees, it will improve both cooling and overall performance for the air duct. Okay, so I think that's all for our discussion and result. Thank you.
In conclusion, this project successfully analyzed the performance of various bend angles in an exhaust duct system under different flow velocities. Through our simulation, we found that the 45-degree bends consistently outperform the 90-degree and 180-degree bends in terms of energy efficiency, pressure drop, and flow stability even at higher velocities. The 45-degree bends resulted in lower turbulence and minimal flow separation, making it the most efficient configuration for maintaining smooth airflow, reducing energy losses, and optimizing system performance. On the other hand, the 90-degree and 180-degree bends show greater flow separation and increased turbulence, leading to higher pressure drops and greater energy dissipation, especially at higher flow velocities. These findings align with the theoretical expectation and highlight the importance of using gradual bends in high velocity system to minimize energy consumption and improve overall system performance. Finally, the result underscore the significance of optimizing duct design to ensure optimal performance, particularly in systems dealing with high flow rates and varying operational conditions. Further, improvement in the system could include minimizing additional shaft turns or investigating more advanced flow optimization technique to further reduce energy losses and maximize efficiency.